In the previous lecture, we have started to deal with the concept of interaction of electromagnetic radiation with matter. In fact, you know that the atomic system is characterized by discrete energy states or discrete energy levels, and usually the atoms in the atomic system occupy the lowest energy state, which is actually called ground state, because you know that in ground state energy is minimum and the stability of the atom is maximum. So an atom in a lower energy state may be excited to the higher energy states through a number of processes. And one of the most important process to excite the atoms from the lower energy state to higher energy state is the process of interaction of the atomic system with electromagnetic radiation. Because when the electromagnetic radiation is incident on the atomic system, the atoms in the ground state may be excited to the excited state due to the absorption of energy from the electromagnetic radiation. Or in other words, you can say the photons of the radiation get absorbed by the atoms in ground state, and gaining that energy, the atoms are excited to the higher energy state. Okay. On the other hand, an atom already in excited state can also make transition to the lower energy state through the emission of electromagnetic radiation. And this emission, you have learnt in the previous lecture, may be spontaneous or stimulated. Actually, this stimulated emission of radiation was predicted by Einstein in 1916 to deal with the equilibrium between the matter and the radiation. Because when we consider only the absorption of radiation by which the atoms moves from ground state to an excited state, and the spontaneous emission when the atoms in the excited state de-excite to the ground state. If you consider only these two processes, then you will see that actually there cannot be an equilibrium between the matter and the radiation at a particular temperature, because in that condition Einstein tried to derive the Planck's law, but he was not successful. So that Einstein predicted a third process, and that third process is called a stimulated emission of radiation. And when along with the absorption of radiation and a spontaneous emission, we also consider the process of stimulated emission of radiation, then it is seen that Planck's law can be easily derived. So that Einstein's prediction was confirmed, that is true, and we in nutshell simply say that when there is an interaction between the matter and the radiation, three distinct processes take place. Okay. In the previous lecture, we have discussed some of the qualitative facts regarding these three processes. So in continuation of the first lecture on this interaction of matter with radiation, this is actually the second lecture on the same subject, and in this lecture we will actually discuss these three processes in quantitative manner. When you discuss these things in quantitative manner, you get actually the concept of Einstein's coefficients, or you can say Einstein's A and B coefficients. Okay. Actually, Einstein has predicted the stimulated emission of radiation, and in dealing with the equilibrium of the matter and the radiation, we are encountered by two types of coefficients predicted by Einstein, and those coefficients are called Einstein's coefficient. And for this, let us consider a two-level atomic system as I have shown in this figure. You can see this first horizontal line marked by 1 is actually the lower energy level having energy E1. Okay, and the second horizontal line which has been marked by this number 2, this is a higher energy level having energy E2. And we consider that in the lower energy level with energy E1, the number of atoms per unit volume is equal to N1. This N1 is what? This is number of atoms present in the energy level 1 or energy level E1, you can say, in unit volume. And similarly, we assume that the number of atoms per unit volume in the energy level 2 or E2 is equal to N2. So N1 and N2 represent the number density, you can say. These are actually the number of atoms per unit volume in the lower energy level and in the upper energy level. Okay. Actually, this assembly of atoms in thermal equilibrium with the radiation actually suffers three distinct processes, and those three distinct processes are a stimulated absorption of radiation, which we will discuss here in some detail. Another is the spontaneous emission, and third one is actually the stimulated emission of radiation. Okay. Now let us consider that this atomic system is interacted with an electromagnetic radiation whose frequency is nu. Here strictly we are considering a monochromatic radiation, or in other words, you can also take that we incident the electromagnetic radiation having frequency lying between nu and nu plus d nu. This d nu is actually very small, so you may assume that the radiation consists of frequency nu. Okay, and the energy density of this radiation we assume is E nu. When you say energy density or spectral energy density, that means what? That is the amount of energy in unit volume. So an electromagnetic radiation having frequency nu and a spectral energy density U nu get interacted with this assembly of atoms. Okay. And as I have told you, when this interaction will take place, then actually three distinct processes takes place, or in other words, you can say that the interaction takes place in three distinct ways. All these things you have studied in the previous lecture. As I have told you, here our aim is in continuation of that first lecture on this subject. We are going to discuss these three processes in some more detail, and our final aim is to discuss the Einstein's A and B coefficient. Okay. So what is the first process? You have seen in the previous lecture that the first process we consider is absorption of radiation. Okay. Now you can see the atoms in the ground state or the lower energy state, see here, marked by this horizontal line 1. These atoms actually, when get interacted with the radiation, let us say a photon having energy h nu is incident on it, and the atom gets energy from that photon, that is the photon is absorbed by the atom. If energy of this photon h nu is just equal to the difference of the energy of two energy levels, that is E2 minus E1, then you know the atom will be excited to the second energy level. Okay. Now our aim is to find what is the probability rate per unit time per unit volume of this transition. Okay. Actually, the number of absorption transition from level 1 to level 2 per unit time per unit volume depends on three factors. And the first one is the number of atoms present in this lower energy level. The second factor is the energy density of the incident radiation, and third one is actually the characteristic of these two energy levels, that is 1 and 2, between which this transition will take place. Okay. In fact, it is seen that the number of transition, if you consider that the number of absorption transition per unit time per unit volume is denoted by the symbol gamma 12. It means if gamma 12 be the number of atoms undergoing absorption per unit time per unit volume from level 1 to level 2. In other words, you can also say that if gamma 12 is the probability rate of occurrence of the absorption transition from level 1 to 2, then as I have told you that this gamma 12 depends on three factors. First one is the number of atoms present in level 1 per unit volume. Second one is the energy density of the incident radiation, and third is the which is actually the characteristic of the two energy levels, that is energy level 2 and energy level 1. That factor depends on the properties of these two levels, and that will come actually as a proportionality constant. In fact, it is seen that the probability rate of occurrence of this absorption transition from level 1 to 2, which I have denoted by the symbol gamma 12, this is directly proportional to N1, and it is also directly proportional to U of nu. Okay. So when you will combine these two results, you will find that this gamma 12 will be proportional to N1 times U nu. Okay. Now when you will remove this sign of proportionality, there must be a proportionality constant. So this gamma 12 is equal to B12 times N1 times U of nu. Here this B12, as you know, this is a proportionality constant, and this is the proportionality constant which depends on the properties of the energy levels E1 and E2. So I have told you that this probability rate depends on three factors. First one is N1, second is U of nu, and third is this B12, because B12 is not a universal constant. It depends on the energy levels E1 and E2. Okay. Actually, this constant B12 is known as Einstein's B coefficient for the absorption of radiation. Okay. Now, the second process which takes place here is called a spontaneous emission of radiation, as you have studied in the previous lecture. In fact, you know that the atoms present already in the excited state. If you consider that the atoms are already in this excited state, then these atoms get de-excited to the lower energy level on its own accord. Nothing influences these atoms to de-excite. This process takes place spontaneously. So, in this case, the rate of transition of the atoms from for the transition 2 to 1 depends only on two factors. Here there is no interaction with the radiation. Okay, no radiation is interacting with the atoms in the excited state. This transition takes place automatically, spontaneously. Okay, so the rate of this transition 2 to 1 will depend only on two factors. First one is the number of atoms N2 present in unit volume of this second energy level. Okay, and the second factor will be again a property which will depend on the properties of the second level and the first level between which the transition takes place. So in this case, the probability rate of downward transition or transition 2 to 1 actually is denoted by the symbol U21, and this U21 is directly proportional to N2. What is this U21? As I have told you that this U21 is the number of atoms making a spontaneous emission per unit time per unit volume, and this is also called the probability rate of a spontaneous emission from 2 to 1, and this is directly proportional to N2 only. And so U21 is equal to A21 times N2. Here A21 is again a proportionality constant, and this proportionality constant again depends on the properties of these two energy levels, that is E2 and E1. So I have told you that this probability rate of a spontaneous emission from level 2 to 1 depends on two factors. First one is the number of atoms per unit volume in the upper energy level, that is in level 2, and the second is this A21. Again you should mark here that this A21 is not any universal constant. It depends on the values of energy of these two energy levels. Okay, so this is the probability rate of a spontaneous emission from level 2 to 1. Okay, if we consider that only these two processes take place, let us consider that is, first process is the transition of atom from lower energy level to upper energy level, and the second process is the transition of atom from upper energy level to lower energy level. If only these two processes take place, in fact before the invention of Einstein, only these two processes were known. So when Einstein applied the considered only these two processes, then he found that the equilibrium between the matter and the radiation is not possible. It means if there is an equilibrium between the radiation and the matter, then this downward transition must be equal to the upward transition. If you consider that this gamma 12 is equal to U21, then it is not possible to derive the Planck's law, or you can say that result will be not in accordance with the Planck's law of radiation or Planck's formula of radiation, which is an experimental fact. So Einstein was compelled to think what actually happens here. And so that Einstein predicted that apart from these two interactions, there is a third interaction too, and that third interaction was predicted by Einstein, which is actually called the stimulated emission of radiation. Okay, stimulated emission of radiation. What actually happens in this case when you say a stimulated emission of radiation, which was actually postulated by Einstein? Actually in this case, if you consider that the atoms are already in the excited state. Okay, then these atoms, when get interacted with the incident radiation, then the field of the incident radiation in fact compel to the atoms in the excited state to return back to the lower energy state. But but remember, the photon of the radiation are not absorbed by the atoms in excited state. These photons only the field of these photons only inspire the atoms to go to the lower energy level. They are not actually absorbed. Okay, so this is just an just an induction. You can say that this is just a induced phenomenon. It means the field of the photon induces the atoms in the higher energy level to transit to the lower energy level. Okay, and in this process, actually the photon's energy, photon's intensity remains unaffected. Okay, and a fresh photon will be emitted due to this transition. So, what will be actually the probability rate of such an stimulated emission of radiation in this case? Actually, the probability rate of stimulated emission of radiation, or you can say that the stimulated emission per unit volume per unit time, actually depends on three factors. The first one in this case will be the number of atoms per unit volume in this excited state, that is N2. First factor on which this probability rate of transition from higher level to lower level depends on the number of atoms N2, which is in unit volume of the upper energy level. The second factor is again the energy density or the spectral energy density of the incident radiation, that is U nu. And the third one is again the properties of these two energy levels between which this transition will take place. So in this case, if you consider that this gamma 21 is the number of stimulated emissions per unit time per unit volume, that is the probability rate of stimulated emission transition from 2 to 1, then this gamma 21 is proportional to N2 and it is also proportional to U of nu. Okay, so when you will combine these two results, you will get gamma 21 equal to B21 N2 times U of nu. Here this B21 is again a proportionality constant, and this is the proportionality constant which depends on the properties of these two energy levels E2 and E1 between which this stimulated emission of radiation takes place, between which this transition takes place. Okay, so I have told you that this rate also depends on three factors, not only two factors but three factors. Okay, and this constant B21 is also called Einstein's B coefficient for the stimulated emission of radiation. Okay, so you can see that when there is an interaction between the matter and the radiation, in fact in that condition three distinct processes takes place, and you have seen what are actually the rate of transition in these three processes. And as I have told you, when this stimulated emission of radiation is not taken into account, then there cannot be in fact the thermal equilibrium between the atomic system and the radiation field. So Einstein predicted this stimulated emission of radiation, And you will see that when we will consider that this process also takes place along with the spontaneous emission, only then equilibrium between the atomic system and the radiation field will be established. Because when we will consider this, then you will see that the result obtained is just in accordance with the Planck's law. And Planck's law is a valid law for the black body radiation or electromagnetic radiation. Okay. So now, if you consider that there is a thermal equilibrium between the atomic system and the radiation field, in that condition, definitely the rate of upward transition and the rate of downward transition must be equal. And what is the rate of upward transition? You have seen that the rate of upward transition is gamma 1, 2. And there are two downward transition. One is due to the spontaneous emission of radiation and another is stimulated emission of radiation. So the total rate of downward transition will be equal to U21 plus gamma T21. Gamma 21. Okay. Now let us substitute the values of these quantities. You have already obtained the values of these, so I am not turning the page. You can remember it. Gamma 12 you have seen this is given by N1 into B12 times U nu. U21 is equal to N2 times A21, and gamma 21 this is N2 times B21 U nu. You have just seen. Okay. Now our aim is to simplify this equation and obtain the value of the energy density of the radiation U nu. Okay. And for this, let us bring this second term in LHS. You can see this U nu will be then as a common factor, and then this will be multiplied by N1 B12 minus N2 B21, and this is equal to N2 times A21. Okay. So you can write U nu equal to N2 A21 and divided by N1 B12 minus N2 B21. Okay. Now let us take this N2 as a common factor in the denominator. So what will happen? This result will be N2 A21 divided by N2 has been taken as common factor, but in first term there is not N2, so we will divide by N2 in the first term, and in the second term there will only B21 will left. Okay. Now this N2 and this N2 will cancel out, and your result is U nu equal to A21 divided by N1 over N2 times B12 minus B21. Okay. Minus. Now we will again take this B21 as a common factor. So you can see, if you take this B21 as a common factor, then the result will be U nu equal to A21 by B21 into 1 over N1 by N2 into B12 by B21 minus 1. Okay. So we have obtained the value of the spectral energy density. Okay. Now our aim is first of all to find the value of this N1 and N2. How we will find the value of N1 and N2? Actually, you know, the distribution of atoms in any energy level is in accordance with the Maxwell's energy distribution law. In other words, you can say that the atomic distribution in energy levels are Maxwellian. So according to Maxwell's energy distribution law, we can write what will be the value of N1 and what will be the value of N2. Okay. So as atomic distribution in energy levels is Maxwellian. Therefore, you can write what will be this N1. You know N1 will be equal to a constant N naught e to the power minus E1 over kT. You know, this is actually Maxwell's energy distribution law. Okay, and similar manner you can write N2 is what? This e to the power minus E by kT is called Maxwell Boltzmann factor. Okay, so this number is actually proportional to the Boltzmann factor, and N2 is equal to N naught e to the power minus E2 over kT. Okay, and as in our equation 4 the term N1 over N2 is present, so you can find the value of N1 over N2 from these two equations. So what will be this N1 over N2? You can see this will be N naught e to the power minus E1 over kT N1 E1 over kT and divided by N naught e to the power minus E2 over kT. Okay. Now this N naught and N naught will cancel out and bring this term in denominator in the numerator. You will get this is equal to e to the power what? E2 minus E1 over kT. Okay, E2 minus E1 over kT. But you have seen that the difference of the energy of two energy levels is just equal to the energy of the photon which is either emitted during the transition from level 2 to level 1. The photon emitted has energy h nu, and this is equal to E2 minus E1. Or when the upward transition takes place, that is from 1 to 2, then you see that the energy absorbed h nu is equal to E2 minus E1. Okay, so at the place of E2 minus E1 you can write h times nu, where nu is actually the frequency of the interacting radiation. Okay, and therefore we can write N1 over N2 will be what? This will be e to the power, see here, h nu over kT. H nu over kT. Say this is equation number 5. Okay. Now let us put this value of N1 over N2 from this equation 5 into this equation number 4. Okay. We will substitute this value here. So see this equation. This factor A21 over B21 will remain same. B12 over B21 will remain same. Only at the place of this N1 by N2 we will now substitute e to the power h nu over by kT. Okay. So let us put it here. Therefore, what will be the expression for u of nu? You have seen that in RHS there is A21 over B21 times 1 over N1 by N2, and at the place of N1 by N2 we will write e to the power h nu by kT times B12 over B21, okay, and minus 1. And what will be the equation number? You will write this is equation 6. So considering the Einstein's postulate of stimulated emission of radiation, we have obtained the expression for the spectral energy density of the radiation. But as you know that Planck's formula for black body radiation already deals with the expression for this energy density, and Planck's formula is experimentally tested, that is experimentally correct. So we can compare this result to the Planck's formula. Okay, so according to Planck's radiation formula, Planck's radiation formula. You can remember, you have studied this Planck's radiation formula in your lower classes, and I have already discussed this formula in the section thermodynamics. So you can see the according to Planck's radiation formula, this U nu is equal to 8 pi h nu cube over c cube times 1 over e to the power h nu by kt minus 1. This is Planck's formula. Now, let us compare these two equations, that is equation 6 and equation 7. Actually, equation 6 was obtained by Einstein considering the stimulated emission of radiation, and this 7 is the well-known Planck's formula. And both of these formula are for the spectral energy density of the electromagnetic radiation. So when we will compare these two equations term by term, what results we will get, you can see easily. So comparing equations 6 and 7, we find, you can see here, in equation 6, the multiple of the factor e to the power h nu by kt is b12 by b21. You can see here. But in equation 7, the multiple of the factor e to the power h nu by kt is simply 1. So you can easily say that this b12 by b21, this is equal to 1. This is equal to 1. This is actually a very remarkable fact, or you can also write it as b12 equal to b21. So these two Einstein's coefficients are not different, they are same. b12 and b21 both are same. What actually physically it means? b12, you know, this is actually the measure of the transition probability of upward transition, that is from the lower level to higher level, that is stimulated absorption of radiation. And b21 is actually the stimulated emission of radiation's constant, and that is from transition from level 2 to level 1, and this is from level 1 to level 2. So actually, when you say that these two are equal, it means that the rate of the upward transition and the rate of downward transition in case of stimulated absorption of radiation and stimulated emission of radiation, both are equal. Okay, so you can say that in presence of the electromagnetic radiation, the probabilities of stimulated absorption and the stimulated emission of atom are equal. So this implies the probability of stimulated absorption and stimulated emission are same. Okay, are same. Now compare the another term. You can see at the place of this A21 by B21 in equation 7, there is 8 pi h nu cube divided by c cube. Okay, so comparing these two terms, we can write A21 over B21. This is equal to what? 8 pi h nu cube divided by c cube. This is actually the relation between the A and B coefficients. Okay, since since B1 to B12 and B21 both are same, so now we will simply write it B because both coefficients are same, and that's why we simply say that there are two Einstein's coefficients, and those are A coefficient and B coefficient, because both B's, that is B12 and B21, both are equal. So there is no need to write B12 and B21. We can simply say that both of these are B. Okay, so in this condition, you can see A21 by B21 is equal to this much. In RHS, you can see that except this nu, all quantities are absolute constant. H is absolute constant, C is absolute constant, 8 pi is absolute constant. So you can easily say that this A21 by B21 is proportional to nu cube. Now you know that this A21 has been written for what? A21 coefficient actually represents the spontaneous emission. Okay, for spontaneous emission we write this coefficient A21, and B21 is written for the stimulated emission. Okay, this is for stimulated emission. Okay, and the ratio of these two coefficients is proportional to nu cube. So if nu is large, and if nu is large, this implies h nu is large. Okay, and as you know that h nu is equal to E2 minus E1. H nu equal to E2 minus E1. So this implies when nu will be large, E2 minus E1, this will be large. Okay, this will be large, and if this is large, you can say that this A21 will be much greater than B21. B21. This is a very remarkable fact. It means if the two energy levels between which the transition takes place, that is E1 and E2, if the difference of energy of these two levels is very large, in that condition, a spontaneous emission will dominate over the stimulated emission. And when a spontaneous emission will dominate, then you will not get the laser light, because laser light is obtained by the stimulated emission, not by spontaneous emission. By spontaneous emission, you have discussed in the previous lecture, we get the ordinary light. We get the ordinary light. So, in this condition, so a spontaneous emission will dominate. A spontaneous emission will dominate. And this is not a favorable condition for the laser production. लेजर प्रोडक्शन के लिए फेवरेबल कंडीशन नहीं है. सो व्हाट शुड बी द कंडीशन so that the situation will be just opposite, that is B21 will be much greater than B21 will be much greater than A21. When this condition will be achieved, only then you will get the laser light. In fact, in the forthcoming lecture, we will discuss how we can obtain this condition. That is, how the stimulated emission will dominate over the spontaneous emission. What condition is required for that, we will discuss in the forthcoming lecture. And till now, you can say that if the energy difference between these two energy levels is smaller, in fact, in that condition, this A21 will be not much greater than B21, or the spontaneous emission will not dominate on the stimulated emission. Okay, so this was all about the Einstein's A and B coefficient. In fact, as I have told you, in the forthcoming lecture, we will see the next concept. First of all, we will see how how amplification can be achieved, and what should be the necessary condition for light amplification, and so that we get the laser light. And as I have told you, for that thing, you must have to obtain a situation when B21 will dominate over A21. Then only you will get laser light. So I think you have understand the idea of the Einstein's A and B coefficient. This is a very important and very basic idea of laser physics. So must watch this video seriously and write down each and every facts in your notebook. Definitely then you will have each and every concept in your mind.